that you're losing money for that ones. So that's the example of it. And next thing that we want to look at it is that how to this one, I believe this is the file. I'm bringing up the file. So this is the example that we worked on. We had the normal probability plots as well in the CHE220. We could show it by NPP, how to draw that. So with the normal distribution curve, when you draw the histogram and you see that it's normally distributed, and then you see that it matches those three rules that we had, like 95% of the data should be between like mu plus minus 2 sigma, or 99 it should be between mu plus minus 3 sigma. So you should cover those ones, and then we say that we have normal distribution curve, or we can draw the NPP first. So with the NPP, the good thing is that we have our rank, like for example, we have 10 data points, and then we find out the xi for all of these ranks, and then the probability of the rank, like from the Z table, and then we try to draw those ones, like based on the expected normal value and the observed value. We can draw this NPP on Excel as well, but I want you to know how to do that, because if you don't know how to do that, make sure that you're going to look at it in your, it should be on the last page of chapter 2, if I'm not wrong, or chapter 1 in the CHE220. We have the notes. Make sure that you know how to draw these normal probability curves, plots, because normal probability plots, it's we need to know the concepts. Then we are going to have a better judgment when we see this. Okay. And now let's see how can we find out these numbers, because these are x. Right? So for the probability of rank, we have this rule. We would say it's I minus 0.5 divided by n. And I is the index, like 1, 2, 3, 4, up to 10. N is the total number of the data. For example, here is 10, right? So we have 10 data points. You see that there are 10. So rank is going to be 10. So we are going to find it like this. So here we can find out P rank by this like equation. Then look at here, we have this one. We would go to the Z table. So these expected values, you will find it from the Z table. We'll find the value from the like for the these are the Z values. Then from these Z values, we can go and read it from the Z table. So it's like that. We find out this. These are the Z values, and then it's like that. You can do that by yourself to find out the Z values. It's like that. What can you do is that, for example, this is the P rank 0.05, right? Go to the table and see that what's going to be the value for 0.05. It's like that. Let me show you, because I've seen that the students, they have this typo as well. So whatever you found out the probability of rank, you would read this, it's here. So find out the value of 0.05 on the body of the Z table, and then read the Z value for it, right? Read the Z value and write down over as expected value for it. And then you would have the right curve, like as observed value and expected value, expected normal value. You will see the curve. If the curve that you have, like if it's like a line, it's like all of the data points, even by eyes when you look at it, if it's like in the, let's say, you can put a tick ruler on it, then we would say that our data points are normally distributed. We would go to the next step. So let me see what's the next. Okay, so expected normal value. Oh, it's written here. Expected normal value on y-axis is the Z value from the table corresponding to P probability of rank. Probability of rank is the cumulative probability value. And normal probability plots are very useful. We will revisit this one in the later chapters. We have normal probability plots versus half normal probability plots. So this is the one that we use it. So the next thing that we want to look is that shape of data and the central limit theorem. Central limit theorem is very important, It's like that you are trying to centralize all the data points that you have. So we do all raw data, we collect, follow the normal. So it's like that we want to know if all of the data points that we collected, those they like collect the normal distribution. No, the answer is no, right? So it's like that whenever you get data, if you get all of the data points and you have the normal probability plot to see that, or you have normal distribution curve to see that if they're normally distributed. If the answer was yes to that one, then you go and you make your regression model. But with the central limit theorem, the beauty in it is that the average of these data points that we get, like samples, set of samples that we get, the average always is normal. Even if the data points that you get is not normally distributed, the average of these data points, like set of samples of data points, they are distributed normal. So we can have the like regression model based on the average of them. Even if I say, and when we say average is X bar. So here, for a random variable X with mean mu and variance sigma 2, so mu and sigma 2 is from population, right? The distribution of the sample mean from a sample size of n on X follows the normal distribution with mean mu and variance of like the sigma 2 over n. So this variance of sigma 2 over n, if you get the square root of it, it's going to be the same as the standard error, or like a standard deviation of the X bar. We call it the standard error. This is true regardless of the shape of the distribution of X. So it doesn't depend on the shape of the distribution of X. The distribution of X bar, no matter what, it is normal. So we have normal distribution for X bar. So whatever model that you want to make based on X bar is going to be a valid one. It's very important, this one, because sometimes you spend millions of dollars and time to gather some data, like let's say critical data, and then your data points are not normal, but the average of them are normal, so we can make our model based on the average of them. So this, at least in part, explains why many measurements do follow the normal distribution. So many of the measurements, in fact, we are measuring the average of the real data. So look at here. So we have 5-bar sample, so you can see that, like, or here it says that we have 5 to 7, let's say. And then you can say sample 1, mean 1, sample 2, mean 2. And these are the data points that we have. So the X and O, O is the actual one, actual data point, and X is the mean of them. So for example, for sample 1, we have like this one, this one, this one, this one, and this one. The mean for the sample 1, so these are the data points, right? The mean for the sample 1 is here, is like 5. And then we try to have it on the right as well. So one thing that you can do is that you can look at this. This is very interesting. Try to connect these zeros like on top. So look what's going to be. It's going to be like, starting from here, it's going to be like this, and then like this, and like this. So it's not normal. But let's look at the average of them. So the average starts from here, right? So it starts from here, go up. So the average is normal. So if you connect the X, like the highest X together, so you will see that the averages are normal, but even the X's are not normal. So that's one of the explanations that we have. And it's because of the central limit theorem. We have other distributions as well. Like, for example, we have an extremely non-normal distribution. You can see we can have like, it starts from here, goes up, and then it goes down. So it's skewed, but it's extremely non-normal distribution. So let's have a summary. A statistic is the science of decision making in the face of uncertainty. And then sample statistic estimates population parameters, fixed yet unknown. Put another way, we analyze the sample and we make inference about the population. So we talked about that. We find out X bar, and then we will say X bar plus minus some margin of error. And we use central limit theorem to find out that margin of error. It's going to be, we're going to talk about that later. like in the next few slides. That's going to give me the population mean. Individual observation may or may not be normally distributed, but averages tend to be normally distributed no matter what. And that's the central limit theorem. The next